accept this invitation to address all of you. My first visit to your college. In fact, I wasn't sure where the location was, although a close friend of mine teaches here. But I've been told about this place because several of my friends and colleagues have come here and addressed you in previous years. So I was always looking forward to this opportunity, and I'm grateful to Dr. Pant to invite me here. The topic kind of chose itself. I've given a talk on this several times at different places. And it's a topic that is not just close to my heart, but it's also an easy topic to understand, because I've picked problems that are relatively easy to understand. There's a lot of number theory which is difficult to explain, just as a lot of other branches of pure mathematics is. But the selection of problems is mostly based on one, a personal choice. You can always complain that there's this very famous problem that one didn't talk about and one didn't include in the list. So it's really at the end of the day a personal choice. But it's also based on the fact that by and large the audience will not have a lot of knowledge, background about number theory. And therefore the problems are being picked in a manner that they're easily accessible in terms of understanding what the problem is. You can't solve a problem if you don't understand it. Okay, that's the first motivation behind picking this. I have probably many more slides than can be accommodated naturally in 60 minutes. So once I kind of run out of time, or I feel that I'm running out of time, I'll probably just breeze through a few slides, and it will be a little difficult to okay. So somebody will have to help me out with how this works. No, that's outside my range. So while that happens, I'll just keep talking. This is quick. Okay, so if you know the password, things are easy. So without further ado, because I know I'm going to run out of time sooner rather than later, let me begin by taking you through my slides, which are solved and unsolved problems in number theory. I will kind of naturally begin with possibly the most famous solved problem there has been in number theory. And I will end with what is possibly the most famous unsolved problem in number theory. Okay, so I hope you enjoy my selection of problems, and I'll begin with a quote or two quotes from one of my favorite books on a biography by one of the favorite mathematicians of mine. I will withhold that for just now, and I will just let you read the quotes, the first of the two quotes. The name of the book is A Mathematician's Apology. Does anybody know who's written that? A very eminent British English mathematician who lived in the latter half of the 19th century and died in 1947. Well, anyway, so I will enjoy letting you read that particular quote.
G.H. Hardy.
This is G.H. Hardy's quote. Excellent. And this is one of my two favorite quotes from that book. There has to be a better way of doing this. Yeah, this is better. The second is also very relevant. I will let you read it. I could read it out for you, of course. A mathematician, like a painter or a poet, is a maker of patterns. If his patterns are more permanent than theirs, it is because they're made with ideas. The mathematician's patterns, like the painter's or the poet's, must be beautiful. Beauty is the first test. There is no permanent place in the world for ugly mathematics. That's G.H. Hardy in The Apology. And this is a book that I highly recommend people to read. A lot of my friends have told me after reading it that they feel depressed. For me, it has exactly the opposite effect. if I'm depressed and when I'm depressed, I read that book. It uplifts my spirit. But really, this is a book written by a mathematician well past his prime. He worked all the way till he was in his 50s, I would say, maybe early 60s. And then when he felt that he was unable to carry out what he really set to carry out, doing mathematical research, and then he started this book. And it was his thesis that you start things like writing books and step away from research when you're at the fag end of your career. That is the time you should devote to less meaningful activities, because for him, the only thing that really mattered was doing research. When he talked about teaching, it was more lecturing rather than teaching. He really didn't like teaching in the regular sense, and he was blessed that he taught in the non-traditional sense because he didn't have to teach the regular undergraduate teaching, which is imparting knowledge. Rather, he lectured more. He was, of course, as you probably know, for the large part of his life at Trinity College, Cambridge. He took some time off, and after Ramanujan passed away, spent a lot of time in Oxford, but then he came back to Trinity College. Anyway, this is not about Hardy. There's a picture from the book, The Apology. It's probably the most standard picture that you would see of Hardy. This is Hardy probably in his late 50s, early 60s. He died at 70. And he had passions outside of mathematics, outside of number theory, and that included cricket. It's a passion I share with him. And one of the things that he wrote, that if he was not going to be a mathematician, then possibly he could have become a journalist. He had good writing skills, or a cricketer. But he also mentions that he would not have been as much of a success in these fields as he was in mathematics. That's his own estimation of himself. I'll begin with possibly the most famous solved problem in number theory. I would say one of the most famous solved problems in mathematics. This was enunciated by the French mathematician, who was a mathematician of many parts, as was the case in those days, 400 years back. Pierre de Fermat, who stated this very famous result. Possibly many of you have seen this before. This was written, as is famously quoted, in the margin of a book, which was discovered soon after he passed away by his son and told to the rest of the world. And it basically mentions something to the effect that this equation x to the n plus y to the n equal to z to the n, when n is at least 3, has no solution in integers. Now here's a problem, a typical problem in number theory, which is easy to understand. There's very little hope or scope for somebody to say that we didn't understand what this meant. But this is typically a problem where things are deceptive. The level of difficulty of the problem is deceptive. And whereas there are any number of problems in number theory, or perhaps in other branches of mathematics as well, which are very difficult to solve, it is not the fact that the problem is difficult that makes this problem important. So one of the importance of this problem has been that aside from all great mathematicians in the past centuries working in it, and of course failing till fairly recently, it is after all a solved problem, it is also true that this has essentially ensured the evolution of a new branch of mathematics, which is the use of algebraic methods in number theory. It's called algebraic number theory. And in the failed attempts to prove the FLT, mathematicians essentially of the later part of the 19th century have built tools which, although have not exactly passed the test to solve this problem, nevertheless, it has been a great tool to solve many other equations of similar nature, and in general, inculcate the study of algebra, bring in the study of algebra into number theory. And therein lies the greatness, perhaps, and the importance of FLT. I'm struggling with this. Well, here's a little picture from Google on Pierre de Fermat. I must mention all these pictures are pictures from Google. I have no real idea if this is who Fermat was. This is what Google tells me, and I am very happy to share that picture. I mention this because I once attended a lecture by a very eminent French mathematician who came to Delhi University maybe about 5 years back. And he coincidentally gave a lecture on a similar topic as this. He didn't title it Solved and Unsolved Problems, but this is essentially what he had. So I went up to him, well, I knew him from before, and I asked him that, I told him that I had a similar presentation, which I've been given over the years. So we shared notes, and I kind of knew what his lecture was about because I just finished attending it. And he said, you would be curious to know that one of the pictures in Google, which is perhaps a picture of Lagrange or Legendre or somebody like that, is actually incorrect. And he's done a lot of research on that and figured out that what Google has against that person is not the right person. It is the person with the same name, same last name, perhaps even a relative, but not the mathematician. And so I must confess that I have no real proof that this is indeed Fermat, but this is what Google tells me. And this is true of almost everybody there, because I've actually seen very few of them in flesh and blood. I couldn't have seen Fermat, goes without saying. This is the first page of the monumental work of Andrew Wiles, which finally proved Fermat's last theorem. This actually became a collector's edition, and I was very happy to collect a copy of that Annals paper. That entire journal, Annals of Mathematics, is one of the foremost journals in mathematics, published by Princeton University Press, which had only 2 articles. The first, single-authored by Andrew Wiles, and the second, which was done in collaboration with one of his ex-students, former students, called Richard Taylor. And the 2 papers together completely nailed FLT. This is about 1995. But because he was a little bit older than the 40, he was not able to get the Fields Medal. Again, maybe I should not go too much into Wiles, but here's a picture of Andrew Wiles. It's a fairly recent picture, maybe about 15 years old, 10 years old. So the definition of recent, of course, will vary. I thought I will talk a little bit about things that are easier to explain. They don't necessarily come in the forefront of too many problems, but there's an entire list of problems that we could talk about really. I don't know how significant they are, but some of them I guess are, about prime numbers. This is the part of the talk where I always change things a little bit. I keep it there because I think this is the one topic that you would understand regardless of what your background is. A quick look at what prime numbers are. I have no doubt whatsoever that you know what the definitions are. So this is what the definition of a prime number is. I have listed 25 of them. There's exactly the first 25, I should say. These are the exact set of primes up to 100. And when I was younger, but just out of high school, I knew these primes all the way till 100. I'd memorized them. And you never know what you need to remember or what you know. And here's an example. In my days, admission to college, to my college, meant that you had to have a certain cutoff, at the end of which you were invited to an interview. And as was the case then, you kind of asked or invited about 5 times as many people as the number of seats for the interview. And you kind of waited the whole day for your turn, and because we waited the whole day and they were running out of time, they invited 5 of us together to face the interview board, which means there was no one-to-one interaction between the interviewers and the candidate. So anyway, so a list of questions, and we were simply asked to introduce ourselves, give a little bit of background, and then write down the answers on a little card, or cue card, or thing. I got done with it, and sensing that I was waiting for the next set of questions, whereas my other candidates, my contemporaries, were trying to write down the answers, one of these gentlemen asked me precisely to write down the primes up to 100. Now that was an unusual question perhaps to ask. But luckily for me, that's exactly something I knew. And therefore, Here's an example of something, the odds and ends which you never know that crops up in life, and it sometimes comes in handy. Sometimes you suddenly find somebody coming to you and saying, well, this is a taxi cab that I rode, and this number is 1729, and it looks unusual, and so on and so forth, and you've just thought about 1729. It's not necessarily true that you know something about 1728 or 1730. You've thought about 1729, you've thought of some properties of 1729, and lo and behold, somebody comes and says, I saw this cab number, and do you think there's something special about it? And there you go, and you say, well, this is the smallest number, there's a sum of two cubes in two different ways. So you never know, these are coincidences, and it's very surprising where something crops up and you suddenly take it from your recesses of memory and bring it out. So this is one of those examples from real life, insignificant certainly, that I can bring out. There are 4 primes up to 10. No, this is not the right way to do it. There are 25 primes up to 100. There are 168 up to 1000, and 1229 up to 10,000. I'm going to run through these because this is just data more than anything else. I managed to put together a set of all primes up to 1000 in one slide. So that's just a slide which lists all primes. You might find that some of them are in boldface. They're all colored the same. Perhaps I could have multicolored it. So the only thing that distinguishes this set of primes are some primes are in regular blue face and the others are in bold face. Can you figure out why I might have put some of them in bold face, not the others? Well, the primes that are in bold face are typically primes that differ by 2. The consecutive primes that differ by 2. So you might even find there are some which are consecutive in bold face. For example, you probably can't see it here. Right at the top, in the first line, you have 3, 5, and 7. So 3 and 5 are a pair of primes that differ by 2. We call them twin primes. And so do 5 and 7. That's the only instance where you will have 3 consecutive odd numbers, all of which are prime. This is not very difficult to prove that this is the only possibility of that happening. Right? So primes is about patterns, pattern recognition. Some of this is easy, some of this is exceedingly hard. It's fair to say that whatever is easy and natural and not that difficult to detect has been detected. So whatever is left for you and me are the things that the older people, the people 500 years back couldn't do. And naturally they're very hard. This is the beginning of everything. Euclid was a master. There's 2 branches of mathematics that we inherit from 2000 years back. One is geometry, and Euclid wrote his very famous book called The Elements in 13 volumes, where he postulated the axioms of geometry. But he also worked in arithmetic, which we now call number theory. One of the famous results of Euclid from 2000 years back is this fantastic proof of the fact there are infinitely many primes. It's an outstanding proof, and what makes it outstanding proof is its simplicity. Okay. It's very difficult to define what is beauty. It's very difficult to define what you like and what you don't like because it's up to you. But what is a beautiful proof, we most often agree, is something that is short, simple to understand, and hopefully can't be better. Hardy writes in his apology and quotes this example as a proof that can't be better. It's simply outstanding. It's a magnificent proof, and you might have seen another 50 other proofs of this. I once lectured on the several different proofs, 16 of them in fact. I had a 20-minute lecture. I could not finish 16 proofs in that time, but I ran through about 8, 10 of them on different proofs of the fact that infinitely many primes. But this one is simply outstanding, can't be better. You have to give this as a first proof, and you have to admit, well, having seen this one, everything else after this is downhill. It's not going to get as good as this. Here's a picture of Euclid, according to Google. He is beautifully attired, matching clothes, color coordinated, and looking sufficiently old. And well, looking like somebody who's got nothing else to do in life but to do some research. Pretty boring looking. Fine. This is a disclaimer. This has nothing to do with the Congress government, nothing to do with other people with the same last name, and I don't have a proof of this. Well, the fact that this was proved in 1971 already precludes a certain gentleman who might be running for leading the government because he was born in 1970. Gandhi was not a very well-known mathematician, but he came to fame perhaps because of this result that he mentioned. I picked this out partly because of Indian connections. There would not be too many Indian names coming up. And partly because it's really a very fascinating result and not very well known. So in the 1966 International Congress of Mathematicians, the one in which they gave the Fields Medal, the one that's held once in 4 years, he announced this result with no proof. One is not trying to say that he didn't have a proof, but he did not give a proof. Not in that Congress at least. A proof came a little later, and once there is one proof, then people latch on and try to pick that proof apart and find a different proof similar to this. And so the first proof I could find by Googling was one that came out in 1971. That proof was not due to Gandhi. The result is. So you could just enjoy the strangeness of this result. But roughly speaking, it says the following. It's recursive, the way you find the nth prime. So P sub n stands for the nth prime. This is standard notation in number theory. And what it says is if I know the first n primes, here's a formula, so to say, to find the n plus 1th. Now it's a fact, not very difficult to prove, that there can be no polynomial, for example, polynomials say in x, where x runs over, say, only the integral values, that will return primes all the time. So it is not expected that you can find a nice enough formula to say, so to say, to represent the prime numbers. So this is something which is completely out of the blue. It has nothing to do with polynomials, and it tells you that if the first n primes are given to you, that I'm not using the pointer, the first term outside the bracket, 2 to the power of Pn plus 1, P sub n plus 1, is the n plus 1th prime. The P sub n plus 1 is the n plus 1 prime there. For this calculation, you need to know what the capital Pn is. It's just the product of the first n primes. And that sum runs over all positive divisors of it. And there's this mysterious function called the Mobius function. I won't explain what that is, but I'll simply say it takes values 0, plus or minus 1, according to some formula. So if you put all of those things, then remember you know what capital Pn is, because you know what the first n primes are. The sum within the bracket can be figured out, because mu is known. And now it's fairly clear that there's at most one power of 2 that can lie between 1 and 2. If you multiply that by the next higher power of 2, it will exceed. It will go outside the limit. If you take this lesser power, it will again go outside the limit. Once it will exceed 2, the other time it will be less than 1. So it's fairly clear there will be exactly one power of 2. And that power of 2, that integral power of 2, is the n plus 1 prime. You can work it out yourself and see. For example, try the first 3 primes, 2, 3, and 5. Plug it into that formula, and lo and behold, you will find exactly 7 satisfying that. It's a curiosity. But once you unfurl the curiosity and read the proof and try to understand it, you will find something which really hits you. It's quite amazing that he thought of what he thought of, because he took a result from 2000 years back. It's called the sieve. And he modulated that, changed it by using some number theory, and got this result. It's a disguised form of what is called the sieve of Eratosthenes. Okay, it's a very, very simple thing that calculates all primes. So I will not go further into that. This is enough for talking about that result. This is a class of primes that have attracted interest over years. This comes back from about 300, 400 years back. Amateur mathematician called Mersenne. These are numbers that look like 1 less than a power of 2. Okay. So people look for numbers of a special type and ask whether it's prime. The reason for that is it's easy to compute some of these numbers to test whether something is prime. So this is one such class of numbers, and these numbers are called Mersenne prime. So Mersenne prime is a number of the form 2 to the power of n minus 1, and it turns out that if it has to be prime, n has to be prime. It's what we call a necessary condition. But it's not sufficient. Life would be very simple if it was, because then you could simply churn out primes forever by putting in a prime, getting a larger prime, 2 to the power of p minus 1, and putting that in to generate an infinite sequence of primes. So that unfortunately is not correct. That whenever you put p as a prime, the 2 to the p minus 1 would be prime. So as is my wont, here is a picture of Perrine Mersenne from Google. Here is a list of Mersenne primes, historically, chronologically dated. It begins, as you can see, from 2000 plus years back. And this is a fairly large list. Let's go to something like 25 years back. The column on the left tells you which is the 31st prime of that form. So we're looking at numbers of the form 2 to the power of p minus 1, where p is prime, and asking the question, is it a prime? The second column is the p. The third column is the number of decimal digits in base 10 for that prime. You can see that you're already going into 65,000 at entry 31. And we're talking about 1985. Lots of progress beyond that. 2009, the 46th Mersenne prime. And here's the last one. This is very tense. This is current knowledge, updated as of a few days back. The stars after 47, the last 4, indicate that the entry at 48 is not necessarily the 48th number in the list. It's the 48th discovered number. Meaning, there's a possibility that there's a prime between whatever the entry at 47 is, some 43 million something, and the entry at 48, which is 57 million and something. There could be a prime in between them, which returns a prime. But we don't know. You can look at the enormity of this computation. The number of decimal digits is already 17 million. Okay. And that was 2013. The very latest thing is a couple of months old, 2018 December. This is the largest known Mersenne prime and the largest known prime. So you go to the book of world records and stuff, or Google, you will find that this is credited, the 51st one is credited with the largest prime number. Not just the largest Mersenne prime. There's another connection between Mersenne primes and what we call perfect numbers. I didn't put that in this set of slides. Perfect numbers are known to the Greeks, numbers like 6 and 28. They have this beautiful property that if you add the divisors of those numbers, you get twice the number. For example, for 6, the divisors are 1, 2, 3, and 6. If you add them up, you get twice 6, 12. The same thing holds for 48. The next one is 496. And you can generate all of them by knowing exactly what the Mersenne primes are. So if 2 to the power of p minus 1, 1 less than 2 to the power of p is a Mersenne prime, and if you multiply it by the lower power of 2 than 2 to the power of p, 2 to the p minus 1, what you get is an even perfect number. And all even perfect numbers are of this form. This is not difficult to prove. If you have a basic knowledge of number theory, you can get through this proof. Here is an analogous result that we don't know the answer to. Whether or not there's an odd perfect number. This is one of the famous unsolved problems in number theory, which I did not include here. I have missed out a lot in the slides. That is one of them. So this is simply a confirmation of what is the largest known prime. It has 24 million and counting decimal digits. It was discovered a couple of months back. More about primes, one of the most famous results in number theory all time. Pi x is how we denote the number of primes up to a real number x. So the number of primes from 1 to x. X need not be a whole number, it could be a decimal, it could be a real number in general. I simply want to count how many primes there are up to x. That is pi x. Here's a little table. This is from probably 50 years back or something, when the computational power was slightly better. It goes all the way in powers of 10 till 10 to the power of 10. The first column tells you exactly how many primes there are up to x. The second column is the mysterious x by log x function. The ln in mathematics usually stands for base e. We often write that as log, but what we really mean is log to the base e. I've written it as ln. It's the same log that you're thinking of. So here's the third column, which tells you what is x by log x, and you're supposed to compare the two, the second with the third. And if you compare the two, you will find that the ratio of the exact answer to this simplified answer tends to 1. This is the most outstanding problem, I would say, in number theory before Fermat's last theorem. Okay. And this also has an important role. This was independently guessed by two mathematicians, one German, of course, and the other French, Legendre. Legendre is not given as much credit for this discovery, but I believe he was equally responsible for guessing what the answer is. Neither of them proved it. Chebyshev, the Russian mathematician, you would have come across his name in other branches of mathematics, including differential equations, for instance, showed that the limit, if it were to exist, would have to be 1. This is all under the assumption that the limit does exist. Here's a picture of Chebyshev. And here is the great theorem, the prime number theorem of number theory. It goes back to 1896, independently proved by two mathematicians. The big part about this result was that was the first time really when a big result in number theory used things outside of traditional number theory. So they used methods from complex analysis. More specifically, they used what is called the Riemann's zeta function, which is a function of a single complex variable, to work out a proof of the prime number theorem. So this is 1896. Well, one of the big results is of course the prime number theorem, but one of the shortcomings of the result was the fact that they used branches, tools from outside of number theory. So therefore, there was always the scope of finding a result, a proof, which did not use tools from outside number theory. It took about 50 years for people to work out that proof. It is officially the result of one person, Atlas Selberg, but the most common perception amongst mathematicians is that it was joint work with Paul Erdős. But because of a variety of reasons, the official proof was actually published only by Selberg. I will not go into the history and things like that. And Selberg was awarded the Fields Medal for this work in 1950. Erdős was not given the Fields Medal, and that was his last chance because he's already 37 in 1950. And when people asked Erdős about his contribution, he kept mum. He never would mention it. It was something that ranked with him all his life. So it's a debatable topic. The theorem itself simply says pi x is asymptotic to x by log x. That simply means that if you take the ratio of the two functions, pi x and x by log x, and take the limit as x goes to infinity, that limit is 1. It does not mean that if you take the difference, that difference tends to 0. Okay, so there's an essential difference between taking the ratio and taking the difference. It is the ratio that tends to 1. Right? So this tells you the approximate rate of growth of that function in terms of a much simpler function. So that rate of growth is x by log x. Okay, it's significantly less than x, but it's significantly more than any power of x less than 1. It's significantly higher than x to the power of 1 minus epsilon for any epsilon equal to 0. It's x by log x. An equivalent result is your nth prime is about n log n. So if you want to figure out where the nth prime is, for large n, it is n log n. Again, in the same sense, as n goes to infinity, Pn over n log n tends to 1. Okay. That's an equivalent statement proving this. Here are the two mathematicians, Adamard and Poisson, who first proved independently about 1896 using complex analytic tools, Riemann zeta function essentially, the proof of the PNT, the prime number theorem. You will find if you look at this that Adamard died at 98, that Poisson died at 96, and the other two gentlemen, Selberg died at 90 and Edish died young at 83. So it is my thesis that if you want to prove the prime number theorem, you better live as long as that. Otherwise you have very little chance of, joining these people. Well, 83 of course is old as well. Another very famous result in amongst prime number results is the fact that if you take any arithmetic progression with the obvious restriction that the first term and the common difference be co-prime, any arithmetic progression, for example 4n plus 1, here the common difference is 4, the first term is 1, or 10n plus 1, these are numbers that end in 1, the first term is 1 again, the common difference is 10, they have to be co-prime. There's an obvious reason for that. This sequence must contain infinitely many primes. Okay, this is again analysis largely. This is due to Dirichlet. But this is analysis which is not really complex analysis. It's more sums and estimations, the ones that you use, for instance, to connect integrals with analysis, with sums. It's that kind of analysis. Picture you will see more than once. This is Dirichlet, died very young, as did many other mathematicians of that era. One of my favorite results about primes, in fact I've given lectures on exactly this result on several occasions. This has certain beauty to this discovery, first discovered by Chebyshev, or first proved by Chebyshev I should say. It was discovered by Bertrand. There's always a prime between n and 2n. It's very deceptively simple, and quite conceivably what people may have done, the founders who discovered this, is gone through a list of primes available to them and found this pattern. Between any n and 2n there's always a prime. And one of the first results that the young Ramanujan did, when he was probably 20 or 22 or something, was to prove this result. It was probably published posthumously after he passed away. But that is probably one of the most famous early results of Ramanujan. He probably didn't have any other results on prime numbers. And then, of course, it was in a sense bettered or simplified by one of my favorite mathematicians. He will come up again and again also. So this is this theorem, Bertrand's theorem proved by Chebyshev. So that person is Paul Erdős. He's going to come up again and again. So Erdős proved this as a young man when he was about 18 years old. And that was his first claim to mathematical fame, proving this theorem of Bertrand that between n and 2n there's a prime. It's an absolutely magnificent proof, and it starts from somewhere you wouldn't think would be the logical start of a proof when you're looking for a prime between n and 2n. But if you've seen this proof several times like I have, then it probably dawns on you that, yeah, this does make sense as to why you would think of that as the first line. It just flows amazingly smoothly. Okay. It's a short proof, it's only about 5 pages or something. I'm going to probably skip this sequence of things because I'm going to probably run out of time. I can already sense that. This is Van der Waerden's theorem. Van der Waerden was a very famous algebraist. Most famous to an undergrad because of his 2-volume book on algebra. So when I was an undergrad, my college library actually had a copy of those books, Algebra 1 and Algebra 2 by B.L. whatever, probably written in the 40s. Fantastic. So your library also has a copy of it. So this, of course, was written pre-recent times, so the notation and so on is a little difficult for us to understand. But nevertheless, it was a classic. Until it was probably replaced by this classic book in the 60s or 70s, the ones that we followed when we were undergraduates. It was a new book then, not so old, by I.N. Erskine, Topics in Algebra. That remained a classic for many, many years. And people who read Erskine's algebra swear by that. Just like you probably swear by Galen or whatever book you follow now. Anyway, digressing. Van der Waerden did only one result in combinatorics. This is more combinatorics than number theory. Okay? So what this basically says is, imagine that you are coloring all the positive integers. I said I wouldn't do this, but this is so close to my heart that I have to tell you something about it. So imagine that you have three colors, red, blue, green, and you're coloring all the integers, either red or blue or green. And I fix a number, say 5, and I ask, is there a number I can go till, starting from 1, so that no matter how I color all the integers from 1 to n in those three colors, red, blue, green. So if I go till 100, and there are 3 possibilities for each color, there's 3 to the power of 100 different coloring schemes. Am I guaranteed a monochromatic arithmetic progression of length 5? You know what an arithmetic progression is? You know what a length of an arithmetic progression is with the number of terms in it? Consecutive terms? All of them would have to have the same color, whether it is red or blue or green. So regardless of how I color this 3 to the power of 100 numbers in 3 colors, and given the pre-prescribed number 5, am I guaranteed that if I go far enough in the sequence, that I can get a monochromatic, meaning all these numbers, these 5 terms, having the same color? The answer is yes. This is the famous result of Van der Waerden, and this is a part of what we call Ramsey theory. It's still in the making. It's about 75 years old, and it is one of my parts of research that I'm fascinated by. It's away from number theory, it's combinatorics, but nevertheless. Van der Waerden never did anything in combinatorics after this result. Here's a picture of B.L. Van der Waerden. You can see that there's a Dutch connection to that name. Maybe he was Dutch, but certainly that name suggests as much. Well, this slide is going to have a lot of Irish. It's a natural thing to have because of a personal, being a personal favorite of mine. There's a famous conjecture of Irish and Turan, which actually I'm going to just let you read and not talk a lot on, because this again leads to a sequence of theorems which is still unsolved and which seems a little bit hard just now. The same picture of Irish I have all the time. Paul Turing didn't live as long. This is the big result towards the conjecture. This is the best we have. This is one of the few persons who's alive in this set of slides. And it's a very recent result. It's only about 50 years old. Parmenides, in fact, was till he retired in the State University of New Jersey, also called Rutgers University. One of the 2 or 3 very famous people in that department. So this is Parmenides' result. This is Green and Tau. This is again an outstanding result for the time. Tau is a very famous number theorist, a very famous mathematician. He worked in several different fields. These are all continuations of the conjecture of Erdős. This is Green and Tau. Both of these people are living. They are very young, in fact. Terence Tau is arguably one of the greatest mathematicians of our generation. He was a prodigy. I could give an entire lecture on Terence Tau, but I will avoid that. In fact, I have a very nice little picture of Terence Tau at the age of 8, mulling over a problem with the 8-year-old Paul Erdős. It's really a fantastic picture to have. You might have seen it. Terence Tau is with the University of California at Los Angeles, and Ben Green, I think, continues to live in the UK. This is the twin prime conjecture. This says there's infinitely many primes, pairs of primes that differ by exactly 2. Certainly one of the most famous unsolved problems in prime number theory. Okay, so I gave you a few of them: 3 and 5, 5 and 7, 11 and 13, 17 and 19, and so on. What this basically says is there's infinitely many such pairs. Very simple to state. Any result in number theory that is easy to state will invite attempts at it. This is a very important and significant attempt. This is not an amateur's work. This is about 1919. Vigo Brute, who showed that if you take the reciprocals of these primes that are parts of the twin prime, and if you add them up, that series unfortunately converges. If it were to diverge, there would have to be infinitely many primes, because if anything that is finite set, and you sum them up, it will have to converge. So because it converges, you conclude nothing. That is unfortunate, because one was hoping that if you took the reciprocals of the primes, which are a part of this conjecture, the twin prime conjecture, they would sum to something which is infinite. That was not to be. Significant progress towards it. I'm going to jump over the Polignac conjecture and tell you about this recent result, 10 years old, that made waves in mathematics and number theory. It was huge. It is also because of the fact that the person who proved it was a nobody. Because generally what happens in mathematics is the persons who prove the big results are the people who are quote-unquote big. They have a history of having proven big results. They come from a family. Their supervisors or the people they've worked with are big people. It is very rare in mathematics to have a pedigree which is not so big and yet give an outstanding result. I'm not talking about general results. Well, Yitang Zhang went to a not so great school, Purdue, which is of course a top 30 school, but it's not a Harvard or a Princeton or an MIT. He had difficulty in finding a job, partly perhaps because he was not a white American. He would have finished his PhD about the time I did, maybe 5 years later. And I could understand the struggles he might have gone through because he was not a Native American in looking for a job. So he did a whole lot of menial jobs just to stay on in the country. Finally found a teaching job in a not so famous place. I think he was in the University of New Hampshire. And then he came up with this result. And of course he became very big once he published this because people took note of what he did. It came from an outsider, somebody who was not expected to be in the forefront of analytic number theory. So anyway, so what he basically proved was there's infinitely many pairs of primes that differ by some large number. So what that upper bound is does not matter. Because he gave a method that could be simplified if you went through the proof and made less and less. So what that implies is that there is some number n, not larger than 7 times 10 to the power of 7. So that there's infinitely many pairs of primes that differ by that number. What you want that number to be is identity 2. We can't make it 2, but we can find some number which is no larger than that, so that the difference of consecutive primes is exactly that, infinitely often. That is what the important this is. So there's a picture of Yitang Zhang, not very old, as you can see, certainly living. Here's Goldbach's conjecture, a very famous result on number theory, something that says every even number is the sum of 2 primes. Again, Christian Goldbach goes back to the mid of the 18th century. His name is associated mostly because he stated it, nothing more than that. He was an amateur mathematician, and perhaps people are kind in giving this name to him because there's stories that say that it's not even due to him, but if I call it some other conjecture, he would correct us. There's progress in this conjecture. 100 years old, Vinogradov proved that there's a weaker conjecture that says every odd number is sum of 3 primes. If you have that, then you're halfway towards proving that if you have every even number is sum of 2 primes. The second one is weaker than the first. If you had the first one, then you could prove the second one. But you don't have the first one, you don't have the even version of it. I only picked one result in here as significant improvements, and that was also about 50 years old, Jinreng Chen, who came very close to proving that every even number is sum of 2 primes. So what he proved was that every even number, every sufficiently large even number, is the sum of a prime and a second number which is either a prime or a product of two primes. So it's either a P1 plus a P2 or a P1 plus P2 times P3. And all of these results require tremendous amount of background knowledge. They require tools well beyond basic number theory, elementary number theory. Very often they require some part of analysis or estimations of sums. And anything that is additive number theory like this is typically borrows on a method that was invented by Hardy and Littlewood. It's called the circle method, to prove these results. And they came about because when Ramanujan spent those 3 years with Hardy, Littlewood was away at war. 1914 to 1918 was First World War, and Littlewood was called away for military duty. So sadly, he was not a part of that association. That is why you only hear Hardy and Ramanujan and not Hardy, Littlewood and Ramanujan. So because of that, his name is not associated. But when he came back from war, Hardy's attempts to prove this fantastic formulas of Ramanujan, some of them were not correct, but most of them were, was why they invented this what is called the circle method. It's a technical thing, it's a little difficult to understand. It requires a little bit of background, I should say. They invented that method to solve an entire class of problems that comes within the realm of additive number theory. This is a classic example of that. So that's the kind of background you require to read all of this up. How much time do I have? 5 minutes. I will end with this and one last slide, which is my last particular thing. This is not a very well-known conjecture, but perhaps in the last 10 years it's gathered ground. It's very simply stated. It's unusual that somebody would have thought of it. It's called the ABC conjecture. Couldn't have a simpler name. Could have even stated something simpler than this. You know what it says? It says, take any 3 positive integers A, B, and C, which are relatively prime, and satisfy A plus B is equal to C. And I'm sure you and I can think of thousands of examples like that, where A plus B is C. And A and B have to be co-prime, that's significant. Then, in any such example, your C cannot be bigger than some constant that depends on epsilon. So for given any epsilon greater than 0, that is a particular constant that depends on epsilon, multiplied by a power of the product of all primes that either go into A or into B or into C to a power which is slightly higher than 1. Okay. Why would somebody think of it? It's very strange. It comes from nowhere. But people began to realize the importance of this. This is about 1985. It's about 85. Because they realized very quickly that if you could prove the ABC conjecture, and this is a conjecture, this is very big in number theory, you could get a toe hold on FLT. You could prove, for example, that there could be at most finitely many exceptions or counters to the FLT. Counters for a fixed n, not for all n. So if you now aggregated all the counters to FLT for all n, this would still possibly be infinitely many. But for a fixed n, there could only be finitely many exceptions. So ABC kind of implies FLT for a fixed n. Now I'm going to jump, and I really don't know how to do this. First, it's probably a picture, a mandatory picture of Masser and Osterley. And I'm going to jump and go to the very last slide. It's sad that I'm going to have to, well actually it's not sad, I'm not going to miss this out. I'm going to show you the most amazing formula there is to see in mathematics. I'm going to stick my neck out and say this is the most amazing formula in all of mathematics. It's of course in number theory, close to my heart. This is the formula that tells you exactly what the number of partitions is for n. Partition of n is the number of ways you can break up n into positive sums. 4, for example, is 4, or 3 plus 1, or 2 plus 2, or 2 plus 1 plus 1, or 1 plus 1 plus 1 plus 1. Exactly 5 ways of partitioning n, of partitioning 4. It all started from Ramanujan, this particular thing. And there's a first paper of Hardy and Ramanujan on the partitions, which I've skipped over, was modified by Hans Rademacher 20 years later. And he came up with this amazing formula which tells you Pn is exactly equal to that obviously convergent series. And it involves everything that you can think of that should have nothing to do with counting. If you look at what is happening inside there, there's a d by dn of something, and what that something is has all sorts of functions that would not involve with something called partitions, with counting. Alright, I had to show you that. It's a page long to just write this down. This is actually accessible to a beginning graduate student. It's contained in a chapter of a book which is available, which you can actually read this if you're interested. And I'm now going to jump to my very last slide, which actually is something which is very hard to explain, except just to state. This is the most famous result in number theory, which is unsolved. One of the most famous results in mathematics. It's called the Riemann hypothesis. And there's plenty of work done in mathematics, assuming the correctness of this. So of course, if this is eventually proven incorrect, a lot of results that we've assumed would be correct would fall down the gutter. It would not be correct. Nevertheless, because we believe that RH holds, we prove results based on the assumption that RH is true. What is the hypothesis? Well, this is the Riemann's zeta function. It's a function of a single complex variable. And following Riemann, we don't call it Z, we call it S. I'm going to have to skip the technical details, which I wrote up, but this is a little difficult. I wouldn't have the time anyway. And I will magically simply state what that result is. But this is not going to make a whole lot of sense if you don't have the background. But technically it says that the non-trivial zeros of the Riemann zeta function lie on that little line. The real part of S is equal to a half. There's a lot of things missing in between that. And what is being said there essentially is to try to explain to you very quickly what is meant by non-trivial, meaning what are the trivial zeros. I'm sorry I don't have the time to explain that. That was not a part of what I wanted to do because I knew that I wouldn't get there. Here's a picture of Riemann. And here's a short collection of books and papers that you might want to read to understand more about this. These are all classics, very, very famous results. Lots of standard results, maybe found in other places which I've missed out. There's a bibliography which is only about 2 pages long. And thank you. And I'm happy to field questions.
Yeah.
5 minutes.
So, any question?
Time.
So it is customary after the lecture that if there is any question.
Well, you don't have to ask a question, but I'd be happy to answer them if I can.
So, I have one question, but before that,
Well, it's more for the audience because, of course, I will see Dr. Pant for some more time. I may not see you after this. So here's your chance to ask a question or two. If you have none, of course, I will answer that. Yes? N to the power of n minus n is equal to
x के power n. तो इसका से मतलब z प्लस में एक ही सॉल्यूशन आता है तो इसके मतलब प्रूव कैसे किया है?
यह मुझे नहीं पता। आप कुछ भी सवाल पूछेंगे और सोचेंगे कि उसका हमारे पास जवाब है, तो ऐसा नहीं है।
ऐसी इक्वेशन आती है
तो डाइफरेंटाइन इक्वेशन जो होती हैं वो काफी कठिन होती हैं सॉल्व करने, आसान नहीं होता है। तो ये वाला मुझे थोड़ा सा सोचना पड़ेगा। हो सकता है बहुत आसान हो सकता है, लेकिन मुझे सोचना पड़ेगा। हमको 5-10 मिनट लगेगा सोचने में कि आसान है कि बहुत कठिन है। कोई भी सवाल जो होता है जैसे आप पूछते हैं, ऐसा नहीं होता है कि उसका तुरंत कोई जवाब दे सकता है। समय लगता है सोचने में कि बहुत आसान है, डिफिकल्ट है, और डिफिकल्ट सवाल बनाना बहुत आसान होता है। यूनिवर्सिटी के जो टीचर्स होते हैं यही करते हैं, बहुत कठिन सवाल देते हैं ताकि आप लोग पास नहीं करें। पूरा इनका लाइफ इसी में बीतता है। तो ये मौका है आपको कि ऐसा सवाल पूछे कि बहुत कठिन है, लेकिन मैं पेपर नहीं सेट करता हूँ, तो मेरे लिए मतलब मुझे बहुत डिफिकल्ट सवाल पूछने से कोई फायदा नहीं है।
आपने सवाल नंबर 3 का पूछा है, क्या है नंबर 3 का?
Can you write it?
n to the power of n, I will speak it out. n to the power of n minus n is equal to x to the power of n का एक ही इंटीजर सोल्यूशन है। मतलब x in z में एक ही सोल्यूशन है। This is what you're saying, right?
ये क्या है? ये प्रॉब्लम है।
I think he's asking a specific question, which is nothing not related to this.
क्वेश्चन कहाँ से है? क्या क्वेश्चन है? आपको क्या चाहिए इसका? एक सॉल्यूशन।
इसका सोल्यूशन चाहिए इनको।
क्या है?
इसका एक ही सॉल्यूशन है, मतलब proof कैसे करेंगे?
इसका प्रूफ कैसे करेंगे ये पूछ रहा है। तो ये तो या तो सॉल्व प्रॉब्लम या अनसॉल्व है, मुझे नहीं पता। मुझे समय लगेगा उस समझने में कि सॉल्व है कि अनसॉल्व है। और ये तो ये बहुत आसान है बनाना सवाल।
आपने बनाई है प्रॉब्लम। आपने बोला तो आपने देखी कि आपने बनाई है प्रॉब्लम। अच्छा नंबर 3 की प्रॉब्लम। इंटीजर्स में आप सॉल्यूशन चाहते हैं।
अच्छा, more specific to my talk, rather than asking me if I can solve a specific problem, I can solve very few problems. So basically, I would rather that I discuss things that I've talked about here.
ये आपने प्रॉब्लम पूछी है ना?
So if you ask me a specific problem, it might be a little hard.
आपके ऊपर कुछ पूछना चाहते हैं?
Somebody else wants to talk about, you can speak in Hindi, that's perfectly fine with me. Somebody else? Alright, so maybe then I will handle your question. Do you have anything for the audience or in private?
My question is, there was Gandhi's result to you.
Yeah.
So it was something you were talking about the P1, P2, Pn are primes.
Yeah, first 10 primes. First 10 primes, yeah.
So next one. So that means between 1 and 2, what you are getting to be power Pn plus 1.
Correct.
So you are getting the next prime actually.
That's right. So if I tell you the first 10 primes.
Or if some integer you are getting may or may not be prime.
Okay, so I don't know how easy it is for me to go back there. That will make more sense if I could go back there. I'm not at all proficient
So
for
this
this.
has been proved. No, I just want us.
Alright, so if I could show this, people would understand what he's asking. So there's this slide right at the beginning, which attributed a result to Gandhi, 1971, and is making some small remarks. It basically said that if you knew the first n primes, not any n primes, then that formula told you how to find the n plus 1th prime. For example, if I knew the first 10 primes, whatever they are, if I knew them, I could find via that formula the 11th one.
But the 11th one would be unique integer.
There's a unique integer, so it looks something like this. You have something in the bracket, which is an expression which depends on the first 10 primes. जो भी था, bracket के अंदर जो भी था, that was a function of the first 10 primes. वो आपने calculate कर लिया, तो जो भी आया, positive कुछ आएगा, वो पक्का है कि positive आएगा, मतलब 0 से ज़्यादा होगा. अब उसको हमको 2 to the power किससे multiply करना है, ताकि अब आंसर जो है 1 और 2 के बीच में आए, ये मुझे पता करना है. जैसे को ब्रैकेट के अंदर आया 0.5 आएगा नहीं, 0.5 नहीं आएगा, और कुछ आएगा 0.5 ही ले लो. अब हमको 0.5 को किससे मल्टीप्लाई करना है, किस पावर से, ताकि रिजल्टेंट 1 और 2 के बीच में आए. वो जो पावर है वो n+1 प्राइम है. जो पावर ले रहे हो इंटीजर पावर ले रहे हो, पॉजिटिव इंटीजर पावर ले रहे हो, फ्रैक्शन नहीं ले रहे हो. So what Gandhi's theorem says is that unique power, uniqueness प्रूव करना बहुत आसान है, क्योंकि दो अलग पावर्स 1 और 2 के बीच में नहीं लाई कर सकते. अगर 2 to the power of 5 1 और 2 के बीच में है, 2 to the power of 6 2 से ज्यादा हो जाएगा, और 2 to the 4 1 से कम हो जाएगा. तो ये जाहिर है कि एक ही पावर उसमें आ सकता है जो कि 1 और 2 के बीच में है. वो पावर जो है वो n+1 पाएगी. ये गांधी जी का मानना है.
It has been proved.
This has been proved. That's not very hard to prove.
So algorithm is also computer algorithm.
This is very straightforward. The formula है, algorithm लिखना तो कोई भी लिख सकता है.
इसका मतलब you can generate all primes.
You can generate all the primes in a very simple way.
That is I wanted to ask.
That's right. You can generate all the primes. It's very straightforward.
So it is computable or not?
Well, it's not computable really, because for figuring out the 100 first, I need the first 100.
It is because computability is also a problem.
It is a problem. Computability is a problem because I need everything before this. Without that, Without that, things become hard.
But computability is still a problem.
Is still a problem because they need everything before that to get to the next one. That is the problem.
Because remember one thing, see, there are problems because I attended a lecture in Porto, Portugal, and there was a person who was doing the work, he is a dynamic, I do not remember the name of it.
Dynamical systems.
From Canada.
Okay.
So they do the research in computability.
Okay.
So Julia set is not computable.
Okay.
Means you cannot find out the Julia set.
Right.
Sometimes, this is a very important branch of mathematics. You want to find out whether some problem is computable or not. So that is also a full branch of it.
Right.
That I was discussing.
Right.
Hence, so any other question?
Yes.
So in third quarter of 2018, it was in the news that Riemann hypothesis has been solved, and it has been claimed by someone called Michael Atiyah.
Okay. See, very famous problems, including the Riemann hypothesis. Please sit down. Is always in the news because somebody or the other wants to claim fame for having resolved it. Usually what happens is there are people who are not very well-known people. They want to be in the limelight. Why this really took people by storm was because somebody of his stature of Sir Michael Atiyah, FRS, Fields medalist, claimed to have found a proof. But he was only 90 years old, and these are not results which are for a person that old. It was very unusual for somebody that old to have a novel method to prove it. You don't prove these results from ab initio, from scratch. By and large, whatever you do, including Yidang Zhang, if you think of what he did, I've attended seminars on what his proof was about in ISI, what, 10 years back, when this result came out, 7 years back. You piggyback on works of others, meaning you understand clearly what others have done before you, and you try to find extensions or simplifications of what they have done. And that is how you do things. You don't do them from scratch. So when Sir Michael Atiyah mentioned this, he made a very, very vague statement कि हमको ये इस्तेमाल करना, वो इस्तेमाल करना, ये इस्तेमाल करना और ये हो जाएगा. Never did he make public the entire proof. So people were very skeptical. But the other thing that we were skeptical about was why did he need to be in the limelight for somebody of that stature? That is not very clear to us. Had he lost his mind at that stage?
Yes.
And he passed away soon after that. When I met him about 20 years back, he came to St. Stephen's College. Dinesh was the director, and he'd invited many of us. He was still a very sharp mind. He must have been in his 60s, late 60s at that stage, early 70s maybe. He was a very sharp mind already at that stage, but maybe by 90 he'd lost it. So this is my take, my personal take on Sir Michael Atiyah's claimed purported proof of this result, of the result that he claimed to have proven.
But he proved one thing. So every
Well, yeah, so
ultimately he proved that he is a human being.
Yes. Yes. Great mind, one of the greatest minds of the century, without a doubt. Absolutely. So many results, famous results named after him. The Fields Medal. No bigger prize than that. 66 Fields Medal, if I'm not mistaken.
Very universal math.
Very universal mathematics, so many different branches. Outstanding mind. You can see that when you speak to him, he can't suppress it. He speaks so fast that it's like thoughts are rushing out. That is the way he speaks. It is kind of the opposite of Erish. When you speak to Erish is very, very slow and very, very thoughtful. And he will speak his words slowly. I've had the occasion of meeting and talking to Erish a few times because a lot of my research is connected with Erish, very intimately connected with Erish. So that would be my favorite person from this set of slides. The others, most of them I haven't seen. I've seen Terence Starr, of course, it's more contemporary. Alright, I'm digressing. Any other questions?
So any other question? So we should thank the professor.